Right now, as you sit there breathing in and out, something invisible is racing toward the planet you are standing on, and almost no one in your neighborhood has the slightest clue. There is no siren outside your window. There is no breaking news alert flashing across your television screen. The sky above your house looks the same as it did yesterday, the same as it did last week, the same as it has for almost every other ordinary afternoon of your entire life. And yet, 93 million miles away, the sun has already done something that, in the silent language of physics, is the equivalent of cocking a loaded gun and aiming it directly at the spinning blue marble we call home. Welcome back to the Cosmic Forecast. I am the voice you have come to trust when the rest of the internet is busy chasing celebrity gossip and forgetting that we live on a fragile rock that is being constantly bombarded by the most violent star in our solar neighborhood. And today, you and I are going to do something different. Today, we are not going to talk in vague generalities about space weather. Today, we are going to look directly at the storm that is, at this very moment, ripping through the vacuum between Earth and the Sun. And we are going to talk about why it is being called a cannibal. Why every space weather forecaster I respect is quietly staring at their monitors with their coffee going cold beside them. And why the official communications you have been receiving feel, to put it gently, incomplete. Because that is the part that bothers me. The science is fascinating, yes. The visuals are spectacular, yes. The auroras that may light up skies far closer to the equator than they have any business doing are going to be absolutely breathtaking, yes. But the part that keeps me up at night, the part that made me sit down and record this episode of the Cosmic Forecast instead of going to bed like a normal human being, is the quiet gap between what scientists actually know about this storm and what is being told to the public. That gap is where rumors grow. That gap is where panic eventually erupts. And that gap is exactly where the Cosmic Forecast lives, in the honest middle ground between sensational doom and dismissive calm. So before we go any further, let me set the table. A Cannibal CME is not a metaphor a journalist invented to sell clicks. It is a real, technical term used by heliophysicists, and it describes a very specific and very dangerous phenomenon. When the sun fires off one coronal mass ejection, that is already a serious event. A coronal mass ejection, or CME, is a billion-ton cloud of magnetized plasma that has been hurled off the surface of the sun at speeds that can exceed several million miles per hour. When that cloud arrives at Earth, it slams into our magnetic field, and depending on how it is oriented, can produce anything from a beautiful auroral display to a planet-wide infrastructure crisis. But a Cannibal CME is what happens when the sun fires off a second, faster CME shortly after the first, and that second cloud catches up to the first one in interplanetary space, swallows it, merges with it, and arrives at Earth as a single, compressed, supercharged superstorm. That is what is happening right now. That is what is heading our way, and that is why I felt I had to make this video. Over the next several hours together, here on the Cosmic Forecast, we are going to break down exactly what a Cannibal CME is, how the current event compares to historical solar storms, what the real risks are to the power grid and to satellites, and to the GPS system that is currently telling your delivery driver where to go, and what you, as an ordinary person sitting in an ordinary home, can actually do to prepare. We are going to talk about the Carrington event. We are going to talk about the Quebec blackout of 1989. We are going to talk about the near miss in 2012 that almost nobody outside of the heliophysics community even remembers. And we are going to talk about why, despite decades of warnings, our civilization has done embarrassingly little to harden itself against the very predictable wrath of our own star. I want you to settle in. I want you to grab a cup of coffee or a cup of tea or whatever you reach for when you are about to learn something that will quietly change the way you look at the sky. I want you to silence your phone, because for the next stretch of time, we are going on a journey that begins on the visible surface of the sun, travels through 93 million miles of empty space, and ends inside the transformer station that powers the lights in your kitchen. And along the way, I am going to show you why the cosmic forecast exists in the first place. Because if there is one thing this channel believes, it is that the public deserves the truth, not packaged, not softened, not sanitized into press release language that says nothing while pretending to say everything. The truth is this: the sun is in the most active phase of its 11-year cycle. The current solar maximum has already exceeded the predictions made by official agencies several years ago. We are seeing more X-class flares, more major CMEs, more geomagnetic storms reaching KP values that used to be reserved for textbook examples. And we are seeing them with a frequency that is making even veteran solar physicists raise their eyebrows behind closed doors. The storm hitting Earth right now is not the first Cannibal CME of this cycle. It will not be the last. Let us begin, not with panic, but with precision. Because if you and I are going to spend the next several hours of your life together examining a phenomenon that most of humanity will never even hear the correct name of, then we owe it to ourselves to start at the beginning, with the bedrock physics, with the fundamental definitions, and with a clear and honest picture of what a coronal mass ejection actually is. No metaphors yet, no drama yet, just the science laid out the way I would want it laid out for me. Imagine for a moment that you could shrink yourself down to the size of a single grain of sand and stand on the surface of the sun. Of course, you would be vaporized in less than a microsecond. So let us pretend, for the sake of imagination, that you are wearing the most ridiculous protective suit ever conceived. From your vantage point on this molten ocean of plasma, you would see a churning, boiling, impossibly violent landscape. You would see arches of glowing material that are taller than the Earth is wide. You would see dark sunspots the size of entire planets. And you would see, looping above the surface like enormous magnetic snakes, structures known as coronal loops, where the sun's powerful magnetic field has captured streams of plasma and is forcing them to flow in great arcs from one magnetic footprint to another. Here on the cosmic forecast, I want you to hold that image, because it is from these loops, from these tangled and twisted magnetic structures, that coronal mass ejections are born. A coronal mass ejection happens when these magnetic field lines, which have been twisting and stressing and storing energy for hours or days, finally snap. The technical term is magnetic reconnection. When two oppositely oriented magnetic field lines are forced close enough to each other, they break their existing connections and reconnect into a new configuration that has a lower energy state. The difference in energy between the old configuration and the new one is released, and it is released catastrophically. The result is a sudden, violent eruption that hurls a vast quantity of solar plasma, along with the magnetic field that was holding it, out into interplanetary space at speeds that can range from a leisurely 400 kilometers per second to an absolutely terrifying 3,000 kilometers per second or more. To give you a sense of scale, let me put those numbers into context. A typical bullet from a high-powered rifle travels at about 1 kilometer per second. A meteor entering Earth's atmosphere travels at around 11 to 70 kilometers per second. The fastest coronal mass ejections, the ones that arrive at Earth in less than a day, are moving at 3,000 kilometers per second. That is 3,000 times faster than a rifle bullet. That is a chunk of magnetized plasma weighing approximately 1 billion tons, moving at velocities that would carry it from New York to Los Angeles in less than 2 seconds. And it is heading, right now, in our general direction, But raw speed and raw mass are not the only things that matter when we talk about coronal mass ejections. And this is where the cosmic forecast is going to start to peel apart the layers that most other news sources are going to leave glued together. What really determines whether a CME is going to give you a beautiful aurora over your house, or whether it is going to take down the power grid of an entire continent, is something called the magnetic orientation of the cloud. Every CME carries within it a magnetic field, and that field has a direction. If the field is oriented in the same direction as Earth's own magnetic field, the two magnetic fields will essentially repel each other. The storm will largely glance off the magnetosphere, and the geomagnetic effects will be relatively mild. But if the magnetic field of the incoming CME is oriented opposite to Earth's field, which we call a southward pointing BZ, then the two fields will reconnect violently when they meet. The storm will pour its energy directly into our magnetosphere, and the geomagnetic effects can be catastrophic. This is the variable that is so often glossed over in mainstream coverage, and it is the variable that I want every viewer of the cosmic forecast to walk away understanding. Because when you hear that a CME is heading toward Earth, your very first question should not be how fast or how big. Your very first question should be, what is the predicted BZ when it arrives? And the honest answer, the answer that almost no government press release is going to give you, is that we genuinely do not know until the storm is less than 30 minutes away from Earth. That is the cruel irony of space weather. We can see a CME leave the sun. We can track it across interplanetary space for days. We can model its arrival time to within a few hours. But the single most important piece of information about it, the orientation of its magnetic field, we cannot reliably measure until it is already on our doorstep, courtesy of a single aging spacecraft called DSCOVR that sits at the L1 Lagrange point and gives us, on a good day, about half an hour of warning. Half an hour, think about that for a moment. The entire global economy, the power grids of 3 continents, the satellites that handle your phone calls, your bank transactions, your military communications, your weather forecasts, your aviation routing, and your turn-by-turn directions home from the grocery store. All of it depends on a 30-minute heads-up from one solitary little probe floating a million miles in front of the planet. That is the system we have built. That is the safety net we are trusting. Now that you understand what a single coronal mass ejection is, let us climb up one more rung on the ladder of complexity and talk about what happens when the sun does not fire just one of these monsters, but 2 of them in close succession. Because that is the situation we are dealing with this week. And that is the situation that earned this particular event the nickname it has been quietly traveling under in the heliophysics community. The Cannibal. Picture 2 waves moving across an ocean. The first wave is large but slow, like a long swell rolling in from a distant storm. Behind it, just minutes later, comes a second wave that is smaller in volume but moving significantly faster. As the faster wave catches the slower one, it does not pass over it or under it. It runs into the back of it, compresses it, piles its own water on top, and the 2 waves merge into a single, towering wall of water that is both deeper and steeper than either of the original waves would have been on its own. That, in extremely simple terms, is what is happening in interplanetary space when a Cannibal CME forms. The cosmic forecast wants you to picture it vividly, because the picture is half the battle when it comes to understanding why this matters. On the sun, this typically happens when an active region, which is a magnetically complex zone usually associated with sunspots, erupts more than once in a short period of time. The sun, in essence, hiccups twice. The first hiccup launches an initial CME outward. That CME plows through the existing solar wind. the constant stream of charged particles that the sun is always blowing outward in every direction. And as it does so, it creates a kind of magnetic tunnel or wake behind itself, where the solar wind is briefly thinner and the path is briefly clearer. When the second CME erupts and follows the same general trajectory, it finds itself traveling through this cleared-out wake, and because it is moving faster and meeting less resistance, it accelerates relative to the first CME. By the time the second cloud reaches the trailing edge of the first, the two are no longer separate events. They have collided, merged, and become a single, hybrid structure that the science community has, with a flair for the dramatic that I respect deeply, decided to call a cannibal. Here is why the cannibal version is so much more dangerous than two independent CMEs hitting Earth one after the other. When the two clouds merge, several things happen simultaneously that turn a moderate storm into a major one. First, the total mass of plasma is now concentrated into a single, denser cloud. Instead of getting hit by 1 billion-ton cloud, and then later by another billion-ton cloud, Earth's magnetosphere gets hit by what is essentially a 2 billion-ton cloud all at once. Second, the magnetic field lines of the two original CMEs get tangled and compressed during the merger, which often produces stronger, more chaotic, and more sustained magnetic fields within the combined structure. And third, the merger process itself often causes the southward component of the magnetic field, that critical BZ value I mentioned earlier, to become deeper and to remain southward for longer periods of time. All three of these factors are bad news for Earth, and all three of them are present in the event that is unfolding right now over your head, even if you cannot see it. Let me also explain something that I think is going to clarify a great deal about why the cosmic forecast keeps emphasizing the danger of this specific storm, rather than the dozens of more routine CMEs we see in a typical month. Cannibal CMEs are not common. In a typical year of average solar activity, we might see one or two events that qualify as cannibals reach Earth. In a quiet solar minimum, we might go years without one. But in an active solar maximum, especially one like the current cycle, which is consistently outperforming the official forecasts, cannibal events become much more frequent. And every time one forms, the upper end of what is possible expands. We are not just rolling the same dice we always roll. We are rolling a die with more sides on it. And some of those sides have outcomes printed on them that our modern, electrified civilization has never actually experienced. There is also a fascinating and slightly unsettling subcategory of cannibal CME that researchers have started to discuss more openly in the last few years. And it involves not two but three CMEs merging together. These triple cannibals, if you want to be informal about it, are exceedingly rare. But the few that have been documented produce geomagnetic storms that punched well above what the individual contributing CMEs would have suggested. Some early modeling of the storm currently approaching Earth has raised the possibility that we are looking at, if not a full triple event, then at least a cannibal with a smaller third disturbance trailing close behind. That is one of the reasons the cosmic forecast is treating this event with the seriousness it deserves. And that is one of the reasons I have decided to dedicate 20,000 words and a full, long-form episode to walking you through the implications. You may be wondering at this point how scientists can possibly tell, days in advance, that two CMEs have merged out in deep space when we cannot directly see the region between the Sun and the Earth in real time. The answer involves a beautiful constellation of spacecraft that you have probably never heard of, but which the cosmic forecast is going to introduce you to as if they were members of your own extended family. If you want to understand why this particular storm is happening at this particular time, you cannot just look at the Sun in isolation today. You have to zoom out and look at the longer rhythm that our star has been beating out for hundreds of years, the slow, regular pulse that scientists call the solar cycle. So let us zoom out together, because the context here is everything. And frankly, this is one of the most fascinating stories in all of astrophysics. The Sun, our enormous, plasma-filled, magnetically chaotic neighbor, goes through a cycle of activity that lasts approximately 11 years from peak to peak. During the quietest part of this cycle, which we call solar minimum, the surface of the Sun can be almost spotless for months at a time. Sunspots are rare, flares are rare, CMEs are rare. The solar wind is steady and uneventful, and space weather forecasters all over the world have a hard time staying awake at their consoles. But over the course of about 5.5 years, the activity ramps back up. Sunspots return. They grow more numerous, more complex, more capable of unleashing energetic events. Flares become more frequent, CMEs become more powerful. And then, at solar maximum, the Sun reaches the violent peak of its temper, and the entire space weather community goes into a state of more or less continuous alertness. This is where we are right now. This is the world that the cosmic forecast has been documenting for you all year. The current cycle is called Solar Cycle 25, because it is the 25th cycle that scientists have been tracking continuously since formal record-keeping began in the 1700s. When Cycle 25 was first predicted by the official forecasting panel several years ago, the consensus prediction was that it would be a relatively quiet cycle, comparable to or possibly even weaker than Cycle 24, which itself had been one of the quietest cycles in a century. The panel suggested that the peak would arrive sometime in 2025 and that the maximum sunspot number would be modest. It was, in retrospect, an extraordinarily conservative forecast. What actually happened is that Cycle 25 began outperforming the consensus forecast almost from the very first year. Sunspot counts came in higher than expected. X-class flares began appearing earlier than expected. The peak appears to have arrived earlier than predicted and at a higher intensity than predicted. By any reasonable standard, the official agencies were caught off guard, and the cycle that was supposed to be a quiet one has turned out to be, well, the cycle of the Cannibal CMEs, the cycle of the unexpectedly violent storms, the cycle that has the cosmic forecast running long-form videos on geomagnetic events at a frequency I genuinely did not anticipate when I started this channel. A dissenting group of researchers, led by a scientist whose work I personally find deeply persuasive, predicted years in advance that Cycle 25 would be a strong cycle. Their methodology relied on analyzing the Sun's polar magnetic fields during the previous minimum, and using the strength of those polar fields to predict the strength of the upcoming cycle. Their forecast was much closer to what we have actually observed than the consensus forecast was. And yet, despite the fact that this alternative methodology has now been demonstrated to be more accurate, the institutional space weather community has been somewhat slow to publicly acknowledge that we are in a stronger cycle than the textbooks predicted. That, friends, is the kind of quiet gap between what is known and what is communicated that the cosmic forecast was created to fill. So why does this context matter when we are talking about a Cannibal CME hitting Earth right now? It matters because the frequency and intensity of CMEs are directly tied to where we are in the solar cycle. During solar maximum, the Sun's magnetic field is in its most tangled, twisted, and unstable configuration. Active regions are larger, more numerous, and more magnetically complex. The probability of any given active region producing multiple eruptions in close succession, which is the precondition for a Cannibal CME, is at its highest. We are not having bad luck with this storm. We are reaping the predictable, mathematically describable consequences of being deep inside the active phase of a stronger than expected solar cycle. And there is another wrinkle. The decline from solar maximum, which is now beginning, is historically associated with some of the largest individual flares and CMEs on record. The Carrington event of 1859, which I am going to discuss in detail in a later segment of the cosmic forecast, did not happen exactly at solar maximum. It happened during the declining phase of the cycle. The Halloween storms of 2003, which I am also going to cover, happened during the declining phase. The pattern is not absolute, and the physics behind it is still being debated, but the statistical tendency is clear. The sun seems to save some of its most spectacular outbursts for the years immediately after its peak. We may, in other words, be entering the most dangerous window of this entire cycle right now. The Cannibal CME currently hitting Earth may be a preview, not a finale. That is a sentence I do not write lightly, and that is a sentence I would not write at all if I were not reasonably confident in the underlying science. There is also a longer rhythm that I want to acknowledge, even if I will not dwell on it. Beyond the 11-year cycle, there appear to be longer cycles of solar activity that play out over centuries. The Maunder Minimum, a period in the 1600s when sunspots almost completely disappeared for several decades and coincided with unusually cold winters in Europe, is the most famous example. Take a deep breath here, because we are about to swing the camera away from the sun and point it at our own planet for a little while. The story of the Cannibal CME is not only the story of what the sun is doing, it is just as much the story of what Earth has, and does not have, to defend itself when these storms arrive. So let me introduce you, in a way that I hope feels both intimate and slightly humbling, to the invisible shield that has been quietly protecting your ancestors, your parents, you, and everything you love for the entire history of our species. Deep inside the Earth, far below the crust we walk on, far below the mantle that drives the slow ballet of the continents, there is a layer of liquid iron and nickel that is sloshing around at temperatures hot enough to vaporize most things we are familiar with. This liquid metal is in constant motion, churning in great convective currents that are driven by the heat of the inner core and shaped by the rotation of the planet. As all of this electrically conductive material moves, it generates electrical currents, and those electrical currents, in turn, generate a magnetic field. That magnetic field stretches outward from the Earth, surrounds the entire planet, and extends tens of thousands of kilometers into space in the direction facing the sun, and far, far further than that in the direction facing away from the sun. We call this region the magnetosphere, and on the cosmic forecast, we have lovingly referred to it more than once as the bubble that lets us exist. Without this magnetic shield, life as we know it on Earth would, frankly, not be possible. The solar wind, that constant stream of charged particles I mentioned earlier, would slowly but persistently strip away our atmosphere over millions of years, much as it appears to have done on Mars long ago. The sun's high-energy radiation would reach the surface in doses that would make the kind of complex multicellular life we represent essentially untenable. The Aurora Borealis and Aurora Australis, which we treat as beautiful spectacles, are the visible signature of the magnetosphere doing its job, deflecting and funneling charged particles down toward the poles, where they collide with atmospheric atoms and produce the eerie glow we so admire. Every time you look at a photograph of the northern lights, you are looking at evidence of a planetary shield in continuous, exhausting operation. But the magnetosphere, magnificent as it is not a rigid wall. It is more like an enormous, flexible bubble, constantly being pushed in by the pressure of the solar wind on the day side, and stretched out into a long, comet-like tail on the night side. Its shape changes constantly, its strength varies. And crucially for our story, when a coronal mass ejection slams into it, the magnetosphere absorbs the energy in ways that can have significant consequences down here on the surface, especially when that CME is a cannibal carrying a stubbornly southward magnetic field. When a CME with a southward BZ hits the magnetosphere, magnetic reconnection occurs on the day side, where the Earth's northward-pointing field meets the incoming southward-pointing field. The two fields essentially merge, and a portion of the CME's energy is dumped directly into the magnetosphere. That energy travels along the magnetic field lines toward the poles, accelerates electrons and ions in the upper atmosphere, drives huge electric currents in the ionosphere, and produces the geomagnetic storms that we measure with the KP and DST indices. Some of that energy also gets stored in the long tail of the magnetosphere on the night side of Earth, where it can be released later in events called substorms, which produce some of the most dramatic auroral displays ever seen. The whole system, from the surface of the Sun to the upper atmosphere of Earth, becomes electrically connected during a major storm, and the effects ripple downward through the ionosphere, into the ground, and into every conductive structure we have ever built. That is the mechanism. That is the chain. That is what the cosmic forecast wants you to picture in your mind whenever you hear the phrase geomagnetic storm. It is worth pausing here to acknowledge something both wondrous and terrifying. The Earth's magnetic field, mighty as it appears to us, is actually relatively weak compared to many of the magnetic fields generated by other planets in our solar system. Jupiter's magnetic field, for example, is roughly 20,000 times stronger than ours. We are protected, but we are protected by a relatively modest barrier, and that barrier was forged by the geological accident of having a hot, churning, conductive core. Other rocky planets like Mars have largely lost their internal heat engines, and with them, their magnetic fields. The fact that we have such a shield at all is, in the long view, a kind of cosmic luck. The fact that we have built a civilization that depends so completely on the steadiness of that shield is, in the long view, a kind of cosmic gamble. There is also evidence, drawn from the magnetic signatures locked in ancient lava flows, that Earth's magnetic field is not constant in strength or direction. It has flipped, completely reversing its polarity, hundreds of times in the planet's history, with north becoming south and south becoming north over the course of thousands of years. We appear to be in a slow weakening phase right now, with the dipole moment of the field declining at a measurable rate over the last few centuries. There is a particular weakened region called the South Atlantic Anomaly, a vast zone over Brazil and the South Atlantic, where the field is unusually weak and where satellites passing through it experience elevated radiation. To understand what the Cannibal CME currently striking Earth is truly capable of, we have to travel backwards in time, to a quiet morning in the late summer of 1859. When an English astronomer named Richard Carrington stood in his private observatory in Surrey and watched, through a small telescope, projecting an image of the sun onto a screen. Something no human being had ever consciously seen before. Carrington saw, with his own astonished eyes, an intense white flash erupt from a complex group of sunspots, brighten the entire visible disk of the sun for a few minutes, and then fade. He had no way of knowing that what he had just witnessed would, within hours, set the world below him on fire in ways that nobody at the time had any framework to comprehend. On the cosmic forecast, when we talk about worst-case scenarios, we are always talking in the shadow of that morning. What Carrington had seen was the visible signature of an enormous solar flare, the most powerful one ever directly observed by a human being up to that point, and arguably ever since. That flare was accompanied by a coronal mass ejection of extraordinary scale, and crucially, one that was aimed almost directly at Earth. And because the solar wind conditions in the preceding days had apparently cleared a path through interplanetary space, much as we discussed in the case of Cannibal events, that CME reached Earth in roughly 17.5 hours, which is several times faster than a typical CME of comparable size. When it arrived, it slammed into the magnetosphere with a magnetic orientation, almost perfectly opposed to Earth's field, dumping its energy directly into the magnetosphere in one of the most intense geomagnetic events in the historical record. The effects that followed, on a planet that had only just begun to build a continent-spanning telegraph network, and that had absolutely no other electrical infrastructure to worry about, were nonetheless astonishing. Auroras were seen across the entire globe, including in latitudes where they had never been seen before and have rarely been seen since. People in the Caribbean, in Central Africa, in Hawaii, and across the southern United States watched in confused wonder as the night sky lit up with shifting curtains of red and green light. In some places, the auroras were bright enough to read a newspaper by at midnight. Birds woke and began to sing, apparently convinced that dawn had arrived. Miners in the Rocky Mountains reportedly woke and started preparing breakfast, only to discover, on stepping outside, that the strange daylight was the sky itself. But beyond the visual spectacle, the storm did something far more significant. It induced powerful electrical currents in the telegraph wires that crisscrossed Europe and North America. Operators reported sparks leaping from their equipment. In some cases, telegraph wires caught fire. In others, machines kept transmitting and receiving, even after the human operators had disconnected the batteries. Powered for a time by nothing but the geomagnetically induced currents running through the wires themselves. Two operators on different continents reportedly held a brief conversation with their power supplies disconnected, using only the energy that the storm was pumping into the global telegraph network. Imagine that. A planetary-scale event so powerful that it ran our communications infrastructure entirely on its own, with no human help. That is the kind of event we now refer to, on the cosmic forecast and elsewhere, as a Carrington event. Now I want to ask you to do something difficult. I want you to take the world of 1859, with its handful of telegraph lines and its modest electrical experiments, and replace it, in your imagination, with the world of right now. Replace those few thousand miles of vulnerable wire with the millions of miles of high-voltage transmission, lines that crisscross every developed continent. Replace those isolated telegraph stations with the hundreds of thousands of transformers, substations, and switching stations that power every city on Earth. Replace that nascent communications technology with the satellite constellations that handle financial transactions, military command, GPS, weather forecasting, aviation, and the everyday acts of looking up directions or reading the news on your phone. Multiply the exposure by every layer of infrastructure that has been built between then and now, and you start to see, in your mind, the shape of what a Carrington-class event would do to us today. The estimates are not subtle. Studies conducted by independent researchers, by industry groups, by insurance companies, and by national academies all converge on similar conclusions. A direct hit from a Carrington-class event today would damage a substantial number of the high-voltage transformers that form the backbone of the power grid. These transformers are not small consumer items. They are individually the size of a house. They are individually custom-built for specific substations, and they have lead times for replacement that can run from months to years, depending on the model and the manufacturer. There are only a handful of factories on Earth capable of building them, and there is no significant inventory of spares ready to be shipped to where they would be needed. If a substantial fraction of these transformers were damaged simultaneously across a continent, the affected regions could be without grid-scale electricity for many months at a minimum, and in worst-case modeling for years. I want to be careful here, because this is where space weather coverage often slides from honest concern into apocalyptic theater, and the cosmic forecast is not interested in joining that crowd. A modern Carrington event would not be the end of human civilization. It would not cause people on the other side of the planet to instantly drop dead. It would not melt the sky. It would not erase the moon. But it would, in the directly affected regions, produce a societal disruption on a scale that we have not experienced in modern memory. Let us pivot from the 19th century to a story most of you have probably never been told, even though it happened well within living memory, and even though it offers one of the clearest, best documented examples of what space weather can do to a modern, electrified society. The date is March 13, 1989. The place is the Canadian province of Quebec. The event is the closest thing to a real-world dress rehearsal we have for what a major geomagnetic storm can do to a developed power grid. And yet it is barely mentioned in mainstream conversation about energy security. The cosmic forecast considers it required viewing for anyone who wants to understand the Cannibal CME story we are unfolding here today. A few days earlier, the sun had unleashed a series of powerful flares and coronal mass ejections from an active region that had grown to enormous proportions. The CMEs raced toward Earth and arrived in the early hours of March 13th. The resulting geomagnetic storm was one of the most intense of the entire 20th century. As the storm developed, it began to induce strong, irregular electrical currents in long conductors at high latitudes, including the high-voltage transmission lines of the Hydro-Quebec power grid. These geomagnetically induced currents flowed into the grid's equipment in ways the system had never been designed to handle. Within 90 seconds, the entire province of Quebec, home to several million people, lost grid power simultaneously in the middle of a frigid Canadian winter night. Let me say that again, because it is one of those facts that benefits from being repeated. In 90 seconds, an entire province went dark, not because of a hurricane, not because of an earthquake, not because of human error or sabotage, because of an event that began on the surface of the sun 2 days earlier. Pause and let that settle in your chest, because this is the kind of thing that mainstream media rarely lingers on. And it is exactly the kind of thing that the cosmic forecast was created to highlight. The blackout lasted around 9 hours for most of the affected population, with full restoration taking significantly longer in some areas. People sat in their dark, cooling homes through the early morning, wondering what had gone wrong. Hospitals switched to emergency generators. Subways stopped. Schools that had been planning normal mornings prepared for cancellations. And in the days that followed, as engineers traced the cause of the failure backward through the grid logs, they discovered that the immediate trigger had been the failure of several large pieces of equipment that had simply not been designed to cope with the kind of induced currents the geomagnetic storm had generated. The equipment had not been faulty in any normal sense. It had performed as designed. The problem was that it had been designed for a world in which geomagnetic storms of that magnitude were treated as a remote possibility, rather than as a recurring engineering reality. Quebec was the most dramatic example, but it was not the only one. The same storm caused problems across the northeastern United States and in parts of Europe. Some transformers showed signs of accelerated wear. Some substations experienced transient failures that were not fully understood for years afterward. Insurance claims related to electrical equipment damage spiked. Long-distance phone networks experienced disruptions. Satellites in low Earth orbit experienced abnormal drag from the expanded upper atmosphere and required orbital adjustments. The tracking and data relay satellite system used by NASA lost communications briefly. Some military satellites went into safe mode. All from a single storm that, by Carrington event standards, was not even particularly large. Why is this story so important for the conversation the cosmic forecast is having with you today? Because it forces us to confront a particular and uncomfortable truth. We do not need a Carrington-class event to produce a significant disruption. We do not need the once-in-a-century superstorm to take down a regional grid. We can do it with a storm that, in terms of pure space weather metrics, is well within the range of what the sun routinely produces during solar maximum. The Quebec event of 1989 was not even the most powerful storm of the 20th century. There were others that, if they had hit at different angles or with different magnetic orientations, would have produced even worse outcomes. In the years since 1989, grid operators in Canada, the United States, and many parts of Europe have made meaningful improvements. They have added geomagnetic monitoring stations. They have installed certain types of capacitor banks and protective equipment designed to mitigate induced currents. They have developed operating procedures for switching configurations during geomagnetic storms. Some utilities now run simulations of major space weather events as part of their resilience planning. These are real improvements, and they deserve to be acknowledged. And this is a very large but the improvements have not been universal. They have not been keeping pace with the growth and interconnection of the grid itself, and in many parts of the world, especially in countries that lack the resources or political will to invest in long-horizon resilience. The grid today is arguably more vulnerable than the Quebec grid was in 1989. There is also a less visible problem that the Quebec story makes painfully clear. Even when the equipment is well designed, even when the operators are well trained, even when the procedures are well drilled, a geomagnetic storm can still hit faster than human reaction times allow. 90 seconds from the first sign of trouble to a province-wide blackout is not a lot of time for any human operator to think, plan, and act. The defense against major space weather events must therefore be automated, pre-positioned, and built into the design of the system itself. History tends to repeat its lessons until we finally listen, and that is something I want you to keep in mind as we move into the next two case studies, both of which sit between the Carrington event and the present day, and both of which the cosmic forecast considers essential to understanding the Cannibal CME currently slamming into our magnetosphere. The first of these is the series of events that the heliophysics community now refers to, with a kind of half-affectionate, half-haunted shorthand, as the Halloween storms of 2003. The second is the storm that almost nobody talks about, even though by some measures it was the most powerful CME of the entire space age, and it happened in 2012. In late October of 2003, an extraordinarily active sunspot region rotated into a position facing Earth. Over the course of about 2 weeks, this region produced a barrage of flares and CMEs that overwhelmed the existing infrastructure for tracking and responding to space weather. Multiple X-class flares were observed, including one event that, by the time the dust settled, was estimated to have been one of the largest flares ever directly measured by satellite instruments. Possibly even saturating the sensors that were trying to measure it. The CMEs that followed swept through interplanetary space, with some of them arriving at Earth in less than a day, hammering the magnetosphere again and again over a span of days. Auroras were seen as far south as Florida and Texas, and in the southern hemisphere, as far north as parts of Australia and New Zealand that almost never see them. The infrastructure impacts were significant and global, even if they did not produce a Quebec-style total blackout. In Sweden, a transformer failure plunged about 50,000 customers into darkness for almost an hour. In South Africa, multiple transformers were damaged by induced currents, with effects that took weeks to fully assess. GPS-based navigation systems experienced significant errors, with positional accuracy degraded for hours at a time. Airlines rerouted polar flights, both because of communications difficulties and because of elevated radiation doses at high altitudes. Satellites experienced anomalies, with several losing functionality temporarily and at least one being effectively lost permanently. Astronauts aboard the International Space Station were directed to take shelter in better shielded portions of the station to reduce their radiation exposure. And all of this happened in a world that, although less dependent on satellites and digital infrastructure than today's, was already deeply tied to electricity and electronics. The Halloween storms taught the space weather community several important lessons, but perhaps the most important was the importance of multi-event sequences. The grid handled the first storm. It handled the second. By the third and fourth, certain types of equipment began to show stress that, individually, no single storm would have produced. This cumulative effect is one of the underappreciated risks of cannibal events and active solar maximum periods. The sun does not always deliver a single massive blow. Sometimes it delivers a series of hard punches, and the cumulative damage can be greater than any individual event would have suggested. That is one reason the cosmic forecast is paying such close attention right now. We are not seeing a single isolated event. We are watching the sun maintain a level of activity that is putting our infrastructure through repeated stress. And we have no good way of predicting in advance which of these events will be the one that finally breaks something important. But the story I really want you to walk away from this segment with is not the Halloween storms. It is the storm of July 23rd, 2012, because this one is the closest call modern civilization has ever had with a true Carrington-class event, and it is, I would argue, criminally underdiscussed in mainstream conversations about space weather. On that day in July, an unusually powerful CME erupted from the sun. It was an extraordinarily fast, extraordinarily dense, extraordinarily magnetized event, and it crossed the orbit of Earth in less than 18 hours. It was, by every available metric, in the same general magnitude class as the Carrington event of 1859. If it had hit Earth squarely, it would almost certainly have produced damage to power grids and infrastructure on a scale that would have made the Quebec blackout look like a warm-up act. Estimates published after the fact suggested that direct global damages could have run into the trillions of dollars, and that recovery times for the worst affected regions could have stretched into years. But here is the part that I want every member of the Cosmic Forecast audience to remember. It did not hit Earth, it missed. Specifically, the CME erupted from a part of the sun that was facing the orbital position that Earth had occupied roughly 9 days earlier. By July 23rd, Earth had moved well past that point in its orbit, and the CME swept harmlessly through the part of space that Earth had been in earlier that month. It did, however, slam directly into one of the stereo spacecraft, which happened to be in roughly the right position to measure it. Were it not for that spacecraft, we would not have a precise record of just how close we came. The sun fired a Carrington-class bullet at Earth and missed by a margin of about 9 days of orbital motion. That is how close we came. That is how thin the line was. That is how little we actually understand about the difference between an ordinary year and a civilization-defining year. The science community published several papers afterward, making the case that this near miss should be treated as a wake-up call. Some of those papers received polite attention from policymakers. Time to bring the camera back to the present, and to the very specific event that brought you to this episode of the Cosmic Forecast in the first place. Forget for a moment the historical case studies. Forget the long arcs of the solar cycle. Let us focus on what is happening above your head, in real time, in this very moment. And let us walk through the data that I have personally been staring at for hours. The active region responsible for the current Cannibal CME has been one of the more impressive complexes of this solar cycle. Over the past few rotations of the Sun, it has been growing in size and magnetic complexity. With a pattern of sunspots that any experienced solar physicist would tell you is a textbook signal of an active region capable of producing major eruptions. Its magnetic configuration has been classified using the standard Mount Wilson and Hale classifications, and by both standards, this region has been carrying the kind of twisted, complex magnetic topology that tends to precede large eruptive events. Multiple flares of M-class and X-class magnitude have been observed in the days leading up to this storm, and at least 2 of those flares were accompanied by full halo CMEs, which is the kind of CME that we observe when a coronal mass ejection is heading more or less directly toward Earth. The first of these Earth-directed CMEs erupted earlier in the week and was tracked across interplanetary space using imagery from a constellation of solar observatories. Its initial velocity was estimated to be in the upper range of typical CMEs, somewhere between 1,000 and 1,500 kilometers per second. Within hours, a second eruption from the same active region launched another CME with an even higher initial velocity. And modeling indicated that this second CME would catch up to the first within a fraction of the journey to Earth. Almost immediately, space weather forecasters began using the word cannibal in their public alerts and internal discussions. The cosmic forecast picked up on these signals quickly, which is why you are now sitting here with me, watching this video, while most of your neighbors are completely unaware of what is unfolding. The combined Cannibal CME, having merged somewhere along its journey, is now in the process of impacting Earth's magnetosphere. The very first effects, the arrival of the leading shock front, were detected by the spacecraft monitoring the solar wind upstream of Earth. The signatures were unmistakable. The solar wind speed jumped suddenly to elevated values. The particle density spiked. The strength of the interplanetary magnetic field rose sharply. And then, after a short delay during which solar physicists held their breath and refreshed their monitoring dashboards, the orientation of the magnetic field swung southward, indicating that the cloud was going to couple efficiently with Earth's magnetic field and dump a substantial fraction of its energy into our magnetosphere. That is the worst-case orientation, the one that makes a storm dangerous rather than merely beautiful, and it is exactly what we are seeing now. The geomagnetic response on Earth has been developing accordingly. The KP index, which is the rough scale that the space weather community uses to summarize geomagnetic activity, has been elevated for hours, and at the time of this recording is sitting at levels that would qualify as a severe geomagnetic storm by the standard scale used by NOAA's Space Weather Prediction Center. The DST index, which is a more physically meaningful measure of how much the storm has disrupted the ring current around Earth, is at levels that have only been seen a handful of times in the last decade. Auroral oval models are showing the boundary of visible aurora pushed unusually far toward the equator, with viewing possible from latitudes that almost never get a chance to see the northern lights. If you live in the northern United States, in southern Canada, in Central Europe, or in similar mid-latitude regions in the Southern Hemisphere. You may well be able to see the aurora yourself tonight, if your weather cooperates and you can get away from city lights. Step outside. Look north or south if you are below the equator. Let the cosmic forecast send you out into the dark with a clear idea of what to look for and what it actually means. But the visible effects, the auroras, are only the most photogenic surface of a much deeper event. Beneath the aurora, the upper atmosphere is heating and expanding, increasing drag on satellites in low Earth orbit and pushing them slowly downward. Their operators are tracking them carefully and, in some cases, adjusting their orbits to compensate. The ionosphere, the electrically charged layer of the upper atmosphere that we use to bounce radio signals around the planet, is becoming turbulent and irregular. High-frequency radio communications, especially over the polar regions, are being disrupted. Pilots flying transpolar routes are experiencing degraded communications, and in some cases, being directed onto alternative paths that keep them away from the highest radiation regions. GPS-based positioning systems are experiencing larger than normal errors. Precision agriculture, surveying, and certain types of automated logistics are seeing intermittent degradation. None of this will appear on the evening news in most countries. None of this will be considered front-page material by mainstream outlets. But all of it is happening in real time, as a direct consequence of the storm we are discussing right now on the cosmic forecast. The power grids in the most exposed regions are also being watched closely. Geomagnetically induced currents are being measured on long, high-voltage transmission lines, particularly in northern latitudes where the auroral electrojet is most intense. Grid operators are running more conservative configurations, holding more reserve generation capacity online, and watching their transformer monitoring systems for any signs of unusual heating, harmonics, or saturation. So far, the reports indicate that the grid is holding up well. Now we arrive at the part of this episode that, if I am being completely honest with you, is the part I have been most reluctant to talk about. Because it is the part that walks closest to territory where conspiracy theorists love to plant their flags, and the cosmic forecast is not in the business of growing flags for them. But there is no honest way to do an episode titled What They Are Not Telling You without addressing, head-on, the very real gap between what the space weather community knows and what the general public is being told. So let us do that carefully, soberly, and with the kind of nuance that I hope you have come to expect from me. To start, let me be clear about what I am not saying. I am not saying that there is a coordinated conspiracy of silence among space weather agencies. I'm not saying that NOAA, NASA, ESA, JAXA, or any other major space weather body is deliberately hiding the truth about solar activity from the public. I have spent years interacting, sometimes directly and sometimes through their publications and public communications, with the scientists and forecasters who work in these institutions. And I have found them to be, without exception, dedicated public servants who genuinely want their work to matter and who genuinely believe that the public should understand what they do. So please, do not walk away from this segment of the cosmic forecast thinking that I am suggesting that anyone is lying to you. That is not where I am going. What I am saying is that there is a structural mismatch between the way space weather information is generated and the way it is communicated, and that mismatch produces, predictably, a set of gaps. Those gaps are not malicious, they are not even intentional. They are the natural consequence of organizational incentives, of communication norms, of the way modern media handles complex science stories, and of the way official agencies are trained to communicate uncertainty. But the result is the same. The public ends up with a picture of space, whether that is consistently and systematically less alarming than the picture that the actual scientific community is staring at on their screens. And that, in my view, is a problem worth talking about, even if the diagnosis is institutional rather than conspiratorial. Let me give you some examples of what I mean. When a major space weather event is in progress, the official alerts that go out to the public are written with extreme care and a strong bias toward avoiding panic. The language is calibrated. The probabilities are softened. The worst-case scenarios are often acknowledged only obliquely, if at all. There are good reasons for this. Agencies that cry wolf too often will not be trusted when the wolf finally arrives. Agencies that produce panic-inducing communications can be blamed for the downstream consequences of that panic. Agencies that talk too openly about worst cases can be accused of fear-mongering by their political overseers. All of these incentives push the public communications toward a kind of professionally cautious calm that, while understandable, often understates the actual nature of the risk. Compare that for a moment to the way the same agencies communicate internally and with the infrastructure operators who depend on them. The notifications that go to grid operators, satellite operators, airline dispatchers, and military commanders are, by all accounts that have been made public, considerably more direct. They include specific predicted impacts. They include specific recommended protective actions. They include estimates of how bad things could get if certain variables turn out worse than expected. They are written for an audience that needs to make real, expensive, operational decisions in real time, and they treat that audience as competent adults who can handle bad news. The cosmic forecast does not have access to those internal communications, and I would not share them even if I did, because I respect the legitimate operational reasons they are restricted. But the existence of that internal communication tier, and the gap between it and the public tier, is something every member of this audience deserves to know about. There is also a deeper issue, which is that mainstream news organizations are, on the whole, not equipped to communicate space weather risk effectively. Most newsrooms do not have dedicated science reporters anymore. Of those that do, very few have anyone who specializes in heliophysics or space weather. As a result, when major events happen, coverage tends to come in two flavors. The first flavor is the giggling, gee whiz, look at the pretty auroras coverage that treats the event as a free fireworks show and pays almost no attention to the underlying infrastructure stress. The second flavor is the breathless, end of the world. The grid is about to collapse coverage that overshoots the actual risk and exhausts the public's attention budget on a storm that turns out to be ordinary. Neither flavor serves you well. Neither flavor reflects the real, calibrated, somewhat bored but still watchful state of mind that the actual experts in the field maintain. And neither flavor gives you, the citizen, the information you need to make sensible decisions about your own preparedness. That is precisely the niche the cosmic forecast has tried to occupy. I am not interested in selling you panic, and I am not interested in lulling you into complacency. I am interested in giving you, in plain language, the honest picture that I would want a friend to give me if our positions were reversed. I want you to know that the storm hitting Earth right now is genuinely significant, but is not a civilization ender. I want you to know that the grid is being stressed, but is unlikely to collapse from this event alone. I want you to know that the auroras are going to be beautiful, and you should go outside and see them if you can. Step with me now into a place most people never get to see in person. Picture an enormous industrial yard at the edge of a town, surrounded by chain-link fencing, full of strange metal structures that look like nothing else in our daily landscape. Tall lattice towers hold up bundles of thick wire. Squat, gray boxes the size of small houses hum quietly in the heat. Insulators stack in glassy columns. Cooling fins line the sides of equipment that, from a distance, looks almost like industrial sculpture. You are standing, in your imagination, in a high-voltage substation. This is where the electricity that lights your kitchen lamp begins its final descent from the long-distance transmission grid into the local distribution network. And this, ladies and gentlemen of the cosmic forecast, is one of the most vulnerable points in our entire civilization when a major Cannibal CME comes calling. The heart of any high-voltage substation is its transformers. These are not the small black bricks that you plug your phone charger into. These are enormous, multi-ton machines, each one designed to step electricity up to extremely high voltages for efficient long-distance transmission, or to step it back down to lower voltages for local use. They are filled with thousands of gallons of specialized insulating oil. They are wound with miles of copper conductor. They are precision-built, often by hand, in a handful of factories around the world, and they are designed to operate for decades with minimal maintenance. They are, in many ways, the unsung heroes of modern life. Without them, the magic of electricity going from a power plant to your refrigerator simply does not happen. And they are also, for reasons that I want to make absolutely clear in this segment, one of the most space-weather vulnerable components of the entire grid. When a major geomagnetic storm is in progress, the rapidly changing magnetic field above the Earth induces electric fields in the ground itself, especially over rocks and soils that have certain conductivity properties. Those induced electric fields then drive currents along any long conductor that has its ends grounded at two different points. High-voltage transmission lines are, in effect, long conductors with their ends grounded through transformers at substations, which makes them excellent unintended antennas for geomagnetically induced currents. These currents are direct currents, not the alternating currents that the grid normally handles, and they can flow through transformers in ways that the transformers were never designed to accommodate. When a transformer experiences a sustained direct current through its windings, it can enter a state called half-cycle saturation. In this state, the magnetic core of the transformer becomes magnetically saturated for part of each AC cycle, which causes the transformer to behave in highly nonlinear ways. It draws unusual amounts of reactive power from the grid. It generates harmonics that ripple through the rest of the system. It heats up significantly, with hot spots forming in places that the cooling system was not designed to handle. In severe cases, the heating can damage the insulation, degrade the oil, distort the windings, and shorten the transformer's life by years, even if it does not fail immediately. In the worst cases, transformers can be damaged catastrophically, with internal arcs, ruptures of the tank, and even explosions. This is the mechanism that took down the Quebec grid in 1989. This is the mechanism that damaged transformers in South Africa during the Halloween storms of 2003. This is the mechanism that has every major grid operator in the world running geomagnetic disturbance procedures whenever a major CME is forecast to arrive. And this is the mechanism that, in a worst-case Carrington-class event, could damage hundreds or even thousands of transformers simultaneously across an affected continent. Hold that image in your mind as we continue this episode of the Cosmic Forecast, because it is the single most important piece of the entire infrastructure puzzle. Now, here is the part that is not often communicated clearly to the public. High-voltage transformers are not interchangeable, and they are not in stock. Each major transformer is essentially custom-built to the specifications of the substation it will live in. The lead time from order to delivery for a new large transformer can run from 12 to 24 months under normal conditions, sometimes longer. The factories that build them are concentrated in a relatively small number of countries, and they operate at close to capacity in any given year. There is no national stockpile of spare transformers ready to be shipped to disaster zones. There is no large international reserve. If 100 large transformers were damaged in a single event across, say, the eastern United States, the question of how long it would take to replace them would be answered, partly, by the question of how quickly the world's transformer factories could ramp up production, and partly by the question of how the limited new supply would be allocated among many competing requests. This is one of the most important infrastructure stories of our age, and yet it is almost entirely absent from mainstream conversations about energy security. We hear endlessly about pipelines and oil tankers. We hear endlessly about the politics of natural gas. We hear about generation capacity, about renewable transitions, about smart meters. We almost never hear about the few thousand large transformers that, in any meaningful sense, hold the entire developed world together. The cosmic forecast believes that this gap in public discourse is itself a kind of failure. You, as a citizen and a voter and a customer, cannot demand resilience investments if you do not know what to demand resilience for. And one of the things you should be demanding after watching this episode is a meaningful increase in the spare transformer capacity of your country's grid. There has been progress, to be fair. In recent years, several countries have begun building modest spare transformer programs. Look up, right now, even if you are sitting indoors. Imagine that the ceiling is gone, that the roof above you is gone, and that you can see clear through into the sky beyond. If you could somehow see, all at once, every artificial satellite currently orbiting the Earth, you would see something that looks more like a swarm than a fleet. Thousands of small, fast-moving points of light, tracing out paths at every conceivable angle and altitude, around a planet that, just a single human lifetime ago, had nothing artificial in orbit at all. That swarm is now the silent backbone of almost every part of modern life, and that swarm is one of the most exposed populations during a major geomagnetic storm. So the cosmic forecast is now going to take you on a tour, briefly but carefully, of what the Cannibal CME is doing to that invisible city above your head. Let us start with the satellites themselves. The most obvious effect of a major geomagnetic storm on satellites is increased atmospheric drag. When the storm deposits energy into the upper atmosphere, it heats and expands. Layers of air that, under quiet conditions, sit comfortably below the altitudes where many satellites operate, can swell upward into orbits that were previously almost vacuum. Satellites that pass through these denser layers experience more friction. They slow down very slightly. Their orbits decay very slightly. Over the course of days or weeks, the cumulative effect of a major storm can drop low-altitude satellites by kilometers, requiring orbital maintenance maneuvers to keep them in their intended positions. The classic example, which I would be remiss not to mention here on the cosmic forecast, was the loss of a substantial number of newly launched Starlink satellites during a moderate geomagnetic storm in early 2022. Those satellites had not yet reached their operational altitudes, and the storm-induced drag pushed them back into the atmosphere before they could climb out of harm's way. The lesson was a costly one, and it has been incorporated into deployment procedures since. The drag issue is just the beginning. Satellites in higher orbits, especially those passing through the radiation belts that surround Earth, can experience elevated radiation doses during major storms. Individual electronic components inside the satellites can be temporarily upset by energetic particles. Solar panels can degrade slightly faster than they would otherwise. Sensitive instruments can be saturated or temporarily blinded. Spacecraft attitude control systems can experience disturbances. And in extreme cases, especially for older satellites whose shielding was designed to less conservative standards, components can be permanently damaged. Operators of major fleets typically have storm mode procedures, where they put their satellites into a kind of defensive crouch during severe events, turning off non-essential systems, repositioning sensitive instruments away from incoming radiation, and waiting out the storm. The current Cannibal CME is, almost certainly, prompting exactly these kinds of procedures in operations centers around the world right now. Beyond the satellites themselves, there is the second layer of vulnerability, which is the data that travels between satellites and the ground. Radio signals that pass through the ionosphere, whether they are coming down from a GPS satellite or going up to a communications satellite, can be distorted, delayed, or scattered when the ionosphere is disturbed. During major geomagnetic storms, the ionosphere becomes turbulent in a way that produces measurable errors in satellite-based positioning and timing services. GPS receivers can lose lock momentarily. Positioning accuracy can degrade from a few meters to tens of meters or more. Differential GPS services, used in agriculture, surveying, and certain transportation applications, can be effectively unusable for hours. Aviation services that rely on precision approach guidance from satellite systems can be forced to switch to ground-based backups where they exist. This is the kind of disruption that, individually, sounds minor. So what if my phone's GPS is off by a few meters for a few hours? So what if a farmer's auto-steered tractor has to switch to manual mode for a season? So what if a few transpolar flights have to fly slightly different routes? Each of these individual disruptions is, in fact, manageable. But when you add them up across a global economy that has come to depend on satellite-based services for everything from financial timestamping to autonomous vehicle navigation to the cellular telephone networks that route your calls and texts, the cumulative impact becomes significant. The cosmic forecast wants you to appreciate that almost every minute of modern life touches at least one satellite-mediated system, and that those systems are all simultaneously degraded, to varying degrees, by major space weather events. Then there is the question of timing itself. The GPS system and its counterparts in Europe, Russia, China, and elsewhere provide not only positioning data but also extraordinarily precise timing signals. Those timing signals are used by communication networks to synchronize their internal clocks. They are used by financial markets to timestamp transactions to the microsecond. They are used by power grid operators to coordinate the operation of generators on opposite sides of a continent. They are used by data centers to maintain consistent timestamps across distributed databases. When ionospheric disturbances degrade GPS timing accuracy, the ripple effects can extend deep into systems that most people have never thought about. The cosmic forecast considers this dependency one of the most underappreciated fragilities of modern civilization. And it is exactly the kind of issue that major geomagnetic storms tend to surface in uncomfortable ways. I want to also mention, briefly, the human dimension of the satellite story, which is the astronauts and cosmonauts currently living and working aboard the International Space Station and other crewed platforms. During major geomagnetic storms and the energetic particle events that often accompany them, the crews of these vehicles can be exposed to elevated radiation doses. Enough of the heavy material, at least for one segment. The Cannibal CME hitting Earth right now is not only a story of risk and infrastructure stress and uncomfortable conversations about communication gaps. It is also a story of one of the most beautiful natural phenomena that human beings ever get to witness with their own eyes. And in this part of the episode, The cosmic forecast is going to do something I do not get to do often enough on this channel, which is to invite you to step outside, look up, and be amazed. The auroras associated with a major geomagnetic storm are not just bigger versions of the lights you see on greeting cards from Iceland or Norway. They are genuinely different in character. During an ordinary night near the auroral oval, the aurora typically appears as a soft, greenish glow on the northern horizon, sometimes forming gentle arcs that slowly shift over the course of an hour. It is lovely, of course, but it is not the kind of thing that grabs you by the shoulders and shakes you. During a major geomagnetic storm, especially one driven by a Cannibal CME with a strong southward magnetic orientation, the aurora becomes something else entirely. It expands across the sky. It pushes far toward the equator. It begins to fold and dance in shapes that resemble curtains, ribbons, and great rolling waves. It develops vivid reds, deep purples, and electric pinks alongside the more familiar greens. And in the most intense moments, during the substorms that punctuate a major event, it can fill the entire sky from horizon to horizon, pulsing in patterns that look almost biological. Why does it do this? The science behind the aurora is, in some ways, just as beautiful as the aurora itself. When charged particles from the magnetosphere are accelerated down along Earth's magnetic field lines, they collide with atoms and molecules in the upper atmosphere. Each of those collisions excites the target atom to a higher energy state. When the atom returns to its original state, it releases a photon of light, with a color that depends on the kind of atom or molecule involved and the altitude at which the collision occurred. Oxygen atoms at altitudes of around 100 kilometers tend to produce the green light that is the most common aurora color. Oxygen atoms at higher altitudes, around 200 to 300 kilometers, tend to produce the rare and dramatic red auroras. Nitrogen molecules tend to produce blues and purples, and the energetic pinks at the lower edges of the curtains. All of these colors, when you see them in the sky, are essentially the cumulative signature of countless individual atomic events, summed together into a glow that we, as observers, perceive as a single coherent display. What you are seeing, in other words, when you stand in your yard during a major aurora, is not an effect. It is a kind of cosmic interaction made visible. You are watching the energy of a coronal mass ejection, sent from the surface of the sun 2 or 3 days earlier, being converted, through the alchemy of magnetic fields and charged particles and atomic transitions, into photons that travel down to your eyes. The aurora is, in this sense, the most intimate and direct visual link between the sun's activity and your personal sensory experience. The cosmic forecast finds this kind of poetic, and I do not apologize for finding it so. The Cannibal CME, currently impacting Earth, has pushed the auroral oval far enough toward the equator that millions of people who normally never get a chance to see the lights are, tonight, going to have one of the best aurora viewing opportunities in years, perhaps in their entire lives. Depending on where you are, you may be able to see auroras from places that almost never see them. Northern parts of the United States, most of the United Kingdom, Central Europe into Germany, Poland, and beyond, southern parts of Canada, mid-latitudes of Australia and New Zealand, maybe even further south or further north than the official forecasts suggest if the storm continues to develop as it has been. Get away from city lights if you can. Look toward the pole. Be patient. Give your eyes at least 15 or 20 minutes to dark adapt. And if the sky cooperates, you will get to witness something that, in a more reverent age, would have been written into legend. While you are out there, you should know that the same storm producing the auroras is also producing a much less beautiful but equally direct effect on radio communications. The high-frequency radio bands, which are still used by aviation, by maritime communications, by amateur radio operators, by certain emergency services, and by various government agencies, can be severely disrupted during major geomagnetic storms. The ionospheric layers that those signals normally bounce off have become disturbed, irregular, and sometimes effectively transparent to certain frequencies, meaning that signals which would ordinarily skip across continents simply punch through into space and disappear. The polar regions are particularly affected, which is why airlines flying transpolar routes will often divert during major storms. The cosmic forecast hears regularly from amateur radio operators who have personally lived through these events, and their accounts of suddenly silent bands during major storms are some of the most evocative reminders that we live downstream of a star. There is also a category of effect called sudden ionospheric disturbances, which are not the same as the broader geomagnetic storm, but often accompany the events that produce these storms. When a major solar flare occurs, the X-ray radiation from the flare reaches Earth at the speed of light and ionizes the day-side ionosphere within minutes. This can cause sudden, complete radio blackouts on the sunlit side of the planet, lasting from minutes to hours depending on the severity of the flare. At this point in the episode, I want to introduce you to a group of people whose work makes everything else in this story possible. They do not appear on magazine covers. They do not have huge social media followings, although a few of them have started to build modest ones in recent years. They typically work in unglamorous government buildings or university offices, often in time zones that are not their own, often in shifts that begin or end while most of us are asleep. They are the operational space weather forecasters of the world, and tonight, while the Cannibal CME is hammering the magnetosphere, they are doing what they always do, which is sitting in front of monitors, drinking too much coffee, and trying to give the rest of us as much warning as the physics allows. The cosmic forecast holds them in genuine admiration, and I want you to meet them. The largest single space weather forecasting operation in the world is run by the United States out of a relatively modest facility in Boulder, Colorado. The Space Weather Prediction Center, a part of NOAA, runs 24 hours a day, every day of the year, with rotating shifts of forecasters who watch the sun, monitor the solar wind, run models, issue alerts, brief customers, and coordinate with international partners. Their primary product line includes the familiar G, R, and S scales that you may have seen referenced in news stories, where G refers to geomagnetic storms, R refers to radio blackouts, and S refers to solar radiation events. Each scale runs from 1 to 5, with 5 being the most severe. The current Cannibal CME is, by most reports, producing geomagnetic conditions in the upper end of the G scale, which is exactly the kind of event their procedures were designed to handle. But the United States is far from alone in this work. The European Space Agency, through its Space Weather Service network, runs a distributed forecasting operation that draws on contributions from research institutions across the continent. The United Kingdom's Met Office operates its own space weather forecasting service, providing dedicated products to the UK government and to commercial customers. Japan's National Institute of Information and Communications Technology runs a respected forecasting operation focused on ionospheric and geomagnetic conditions. China, India, Russia, Australia, South Africa, and many other countries operate their own monitoring and forecasting capabilities, and most of these national efforts coordinate, at least informally, through international organizations such as the International Space Environment Service and the Committee on Space Research. The cosmic forecast deeply respects this international cooperation, which has, over decades, built up a remarkable, distributed, planetary nervous system for watching our own star. What does a typical day on the operations floor of one of these centers look like? It looks like a wall of monitors showing real-time imagery from solar observatories, plots of solar wind parameters from upstream spacecraft, magnetograms from ground stations around the world, and a variety of model outputs that try to predict everything from the arrival time of incoming CMEs to the strength of induced currents in transmission lines. It looks like a forecaster, headset on, talking simultaneously to a grid operator in one region, an aviation dispatcher in another, and a satellite operations team in a third. It looks like decisions being made in real time, with imperfect information, under time pressure, with consequences that can ripple outward to billions of people. And it looks like a great deal of patience, because the truth of operational space weather, like the truth of operational meteorology, is that most of the time, nothing especially dramatic is happening, and the work consists of carefully monitoring conditions that may or may not develop into something significant. When a major event does occur, the tempo on the operations floor changes. Forecasters move quickly, but not in the chaotic way that movies tend to portray. They run through procedures that have been refined over decades. They issue alerts in carefully calibrated language. They brief their customers. They run additional models. They cross-check their interpretations with colleagues in other countries. And then, when the storm is fully underway and there is nothing more to do but watch, they settle into the long, attentive hours of monitoring the response of the geomagnetic field, the behavior of grid operators, the status of satellite fleets, and the unfolding effects on radio communications and the upper atmosphere. There is, in this work, a particular blend of urgency and slowness that, in the cosmic forecast's experience, very few professions match. I want to highlight also the role of academic and amateur observers in the broader space weather ecosystem. There are universities around the world that operate observatories, magnetometer networks, ionospheric monitoring stations, and other instruments that feed into the global picture. There are individual researchers who specialize in particular pieces of the puzzle, such as the magnetic configurations of active regions, or the propagation of CMEs through interplanetary space, or the dynamics of the ionosphere during major storms. And there is a worldwide community of amateur radio operators, amateur astronomers, and citizen scientists who contribute observations and data that, taken collectively, add a remarkable layer of resolution to the official monitoring networks. The cosmic forecast wants you to know that this is, in many ways, a deeply democratic field, where individuals with relatively modest equipment can still make meaningful contributions to a problem of global significance. What I find personally most moving about the forecasting community is the long-term perspective that pervades it. The people who work in this field tend to think in terms of solar cycles rather than news cycles. They tend to remember the storms of the 1960s as if they were last year's events, because to them, in the grand timeline of solar variability, they essentially are. They tend to be humble about what we know and what we do not. All right, here is the part of the episode that I think a lot of you have been waiting for, even if you would not have phrased it this way at the beginning of the video. Up to now, the cosmic forecast has walked you through the science, the history, the politics of communication, and the broader infrastructure picture. That is all valuable, and I would not change a moment of it. But the practical question that brought you here, the question that is sitting in the back of your mind as you watch the Cannibal CME unfold above your head, is the question of what you, personally, sitting in your home with your own family and your own situation, can actually do about it. So let us talk about that, soberly and without selling you anything. First, let me say what I am not going to do. I am not going to tell you that you need to spend tens of thousands of dollars on an off-grid bunker, that you need to abandon civilization, or that you need to stockpile so much food and water that your home becomes unrecognizable. I am also not going to pretend that nothing is needed. The truth, as is so often the case, sits in a sensible middle position, and that is the position the cosmic forecast wants to help you find. A good first step is to understand the actual range of likely outcomes from major space weather events, so that you can size your preparedness appropriately. For the kind of Cannibal CME that is hitting Earth this week, the practical consequences for most individuals are likely to be limited to brief disruptions in GPS, occasional issues with high-frequency radio communications, a small chance of localized power problems, and an excellent chance of seeing the aurora if your weather cooperates. That is the realistic spectrum. You do not need a bunker for this storm. You need patience, a charged phone, and a willingness to step outside and look at the sky. For the broader class of events, including the rare but real possibility of a Carrington-class event sometime in your lifetime, a more substantial baseline of preparedness is, in my view, justified. But, and this is the important point, the preparations that protect you against a major space weather event are essentially the same preparations that protect you against any extended infrastructure disruption. Whether caused by space weather, severe storms, earthquakes, cyber events, or anything else. The cosmic forecast believes that thinking in terms of generic resilience, rather than space weather-specific resilience, is the most rational and humane way to approach this. You are not preparing for the sun. You are preparing for the possibility that the modern world you depend on may, for various reasons, be unavailable to you for a stretch of days or weeks at some point in your life. Phrased that way, the case for moderate, sensible preparedness becomes much easier to make to yourself and to the people you love. A reasonable household preparedness baseline, in my opinion, includes the following. A supply of drinking water that would last your household for at least 2 weeks under reduced consumption, which works out to roughly 1 gallon per person per day, although you can stretch that. A supply of non-perishable food that does not require refrigeration or extensive cooking, again sized for at least 2 weeks. A means of cooking that does not depend on the electrical grid, whether that is a propane camp stove, a small wood stove, or simply the ability to prepare meals cold. A way to keep warm in winter and cool in summer that does not depend on grid electricity, recognizing that the latter is much harder than the former. A first aid kit and a reasonable supply of any prescription medications that members of your household depend on. A flashlight or two with spare batteries. A battery-powered or hand-cranked radio so you can receive emergency broadcasts. Some cash in small denominations because electronic payment systems may be unavailable. A plan for communicating with family members if cellular networks are down. And most importantly, a sense of community with your neighbors, because in any extended disruption, the people physically nearest to you are the people most likely to be in a position to help. You will notice that I am not suggesting anything especially exotic. I am not suggesting that you build a Faraday cage in your basement. I am not suggesting that you wrap your electronics in aluminum foil during major storms. The cosmic forecast does not believe that household-scale electronic protection is a high-priority concern, even during major events. Because the kinds of induced currents that damage continent-scale transmission lines do not directly damage the kinds of small electronics in your home. Your phone is not going to explode during a geomagnetic storm. Your laptop is not going to catch fire. If the grid goes down, the most likely outcome for your home electronics is simply that they will be without power, not that they will be physically destroyed. There are, however, a few specific habits I would recommend for major space weather events. Keep your phone and other essential devices charged when a major storm is forecast, so that if there is a brief power interruption, you have a buffer. Keep your vehicle's fuel tank reasonably full, because fuel pumps depend on grid electricity, and an extended outage can mean an extended inability to refuel. Know where your circuit breaker is, and how to safely disconnect your home from the grid if local authorities request it. Although in most jurisdictions the actual decision is made upstream by utility operators. And perhaps most importantly, know how to live without your screens for a few hours or days if you have to, because the psychological challenge of an unexpected disconnect can, for many people, be at least as difficult as the practical inconveniences. Pulling the lens back even further now, let us talk for a stretch about what is happening or not happening at the level of governments and international institutions. Because the question of civilizational resilience to space weather is fundamentally a question of policy as much as it is a question of physics. The cosmic forecast has covered policy themes before, and I have always tried to do so in a nonpartisan way, focused on outcomes rather than ideology, and I am going to take the same approach here. For most of the 20th century, space weather was essentially a niche concern within a small slice of the scientific community. The infrastructure was less interconnected, the dependence on satellites was lower, and the political incentive to invest in resilience was correspondingly modest. The Quebec blackout of 1989 began to change that, although the changes were slow and uneven. The Halloween storms of 2003 accelerated the shift somewhat, particularly within the United States and parts of Europe. And in the years since, especially since the publication of several major studies estimating the potential economic impact of a Carrington-class event, space weather has gradually moved from the periphery of policy discussions toward something closer to, although not quite at, the mainstream. In the United States, several presidential directives and executive orders have been issued over the past 2 decades that explicitly identify space weather as a national security and economic security concern. The National Space Weather Strategy and the related action plan provide, at least on paper, a framework for federal agencies to coordinate their work in this area. NOAA's Space Weather Prediction Center has had its responsibilities expanded. The Department of Homeland Security has incorporated space weather into its broader critical infrastructure protection planning. NASA has invested in new observational missions. The Department of Defense has its own internal space weather operations. These are real and meaningful institutional developments, and they should be acknowledged. But, and here is where the cosmic forecast wants to be honest with you, the gap between policy on paper and resilience on the ground remains very large. Many of the most impactful actions that would reduce the vulnerability of the United States to a major space weather event involve investments in the electrical grid, in the spare transformer supply chain, in regional resilience planning, and in coordination across the patchwork of investor-owned utilities and public power authorities that actually run the grid. These investments are expensive, they have long payback periods, they often require regulatory changes that are politically contentious, and they compete for attention with shorter horizon concerns. The result is that progress has been real but slow, and the pace of progress has not, in my opinion, kept up with the pace of Solar Cycle 25. The story in the United Kingdom and the European Union is broadly similar. Space weather has been incorporated into national risk registers, which is a meaningful step. Coordinated forecasting capabilities have been strengthened through ESA programs and individual national efforts. There are ongoing research projects on grid resilience, satellite hardening, and ionospheric monitoring. But again, the actual hardening of the underlying infrastructure has lagged behind the recognition of the risk. The United Kingdom's place on the global grid, particularly its dependence on submarine cables and on transformers concentrated at specific substations, creates particular vulnerabilities that have been studied but not, as far as public information allows me to judge, fully addressed. In other parts of the world, the situation is significantly more concerning. Many countries do not have dedicated space weather forecasting capabilities at all, and depend on products distributed by NOAA, ESA, or similar organizations. Many countries do not have grid infrastructure that has been designed or upgraded with geomagnetic disturbances in mind. Many countries lack the political bandwidth to prioritize a risk that, on average, does not produce a major event in any given year. The result is a deeply uneven global resilience posture, where the impact of a major space weather event would depend not only on the physics of the storm, but also on the geography of the grid and the policy choices of the countries it affects. The cosmic forecast finds this unevenness deeply problematic, both as a matter of justice and as a matter of practical concern, because in a globally interconnected economy, the failures of one region's infrastructure can cascade into others in ways that are hard to predict in advance. There is also an international institutional dimension that I want to highlight. Several international bodies, including the International Space Environment Service, the Committee on Space Research, and the World Meteorological Organization, play important roles in coordinating space weather monitoring and forecasting across national boundaries. The International Space Environment Service is particularly important, as it operates a distributed network of regional warning centers that exchange data and coordinate alerts on a continuous basis. Without this kind of international cooperation, the global picture of space weather would be much harder to assemble. The cosmic forecast considers this cooperation one of the quiet success stories of modern science diplomacy, and it deserves more public recognition than it typically receives. One specific policy area that I want to call out is the question of insurance and financial risk. Major reinsurance companies have, in recent years, begun publishing analyses of the potential economic impacts of severe space weather events. Some of these analyses estimate that a Carrington-class event hitting a developed economy directly could produce damages in the trillions of dollars, depending on the duration of grid outages and the resulting cascading failures. These estimates are inherently uncertain, but they have begun to influence how insurers think about correlated risks across their portfolios. There is a quiet, ongoing conversation in the reinsurance industry about whether and how to underwrite space weather risk. And the outcomes of that conversation may eventually shape capital flows in ways that incentivize, or fail to incentivize, the kinds of resilience investments that are needed. Let me turn now to a more hopeful subject, because the cosmic forecast does not believe in leaving you in the dark, in any sense of that phrase. While the risks of major space weather events are real, and the gaps in our preparedness are significant, the science and technology of understanding and responding to those events have been making genuine progress in recent years, and there is more good progress on the horizon. So let us spend a segment talking about the future, and about the reasons for grounded, technically literate optimism, alongside the legitimate concerns we have been raising. The most immediate area of progress is in observation. The constellation of spacecraft watching the Sun and the inner solar system is the most capable it has ever been in human history. The Parker Solar Probe has, in the years since its launch, repeatedly flown closer to the Sun than any other artificial object, returning data from inside the corona itself. the region where the solar wind is born, and where the magnetic structures that eventually become CMEs first take shape. The Solar Orbiter mission, a collaboration between ESA and NASA, has begun delivering the first detailed images of the Sun's polar regions, which have long been a blind spot in our observations, and which appear to play a crucial role in setting up the magnetic configurations that drive each solar cycle. The Solar Dynamics Observatory continues to provide exquisite high-cadence imagery of the Sun in multiple wavelengths. The constellation of GOES satellites monitors space weather from geostationary orbit, and new missions are being planned that will further fill in the gaps. The cosmic forecast finds this trajectory profoundly encouraging, even if the rate of progress is sometimes slower than the field would prefer. A particularly important area of upcoming improvement is in space weather forecasting from upstream positions. The current dependence on a single, aging spacecraft at the L1 Lagrange point, namely DSCOVR, with limited backup, is one of the most uncomfortable single points of failure in the entire global space weather system. New missions are being planned that will provide additional measurement capabilities at L1 and at other positions, potentially including the L5 Lagrange point, which would provide a side view of the inner solar system and would allow much earlier detection of Earth-directed CMEs and active regions. If even one or two of these proposed missions are deployed in the next decade, the early warning time available to forecasters and infrastructure operators could be meaningfully extended. There is also progress on the modeling side. Numerical models of the Sun's atmosphere, of CME propagation through interplanetary space, and of the response of Earth's magnetosphere to incoming storms have been improving steadily for decades. And the rate of improvement has been accelerated in recent years by the increasing availability of computational power and by advances in machine learning. Some of the most interesting recent work in the field uses machine learning techniques to improve the accuracy of CME arrival time forecasts, to identify subtle precursors of major flares in solar imagery, and to predict the geomagnetic response of the magnetosphere from upstream measurements. These improvements may seem incremental from the outside, but they translate directly into more accurate alerts, more reliable infrastructure protection actions, and ultimately into fewer cases where a storm produces damage that better forecasting could have helped prevent. On the engineering side, there is meaningful progress in the design of infrastructure that is more robust to geomagnetic disturbances. New types of capacitor banks and series compensators are being deployed on certain high-voltage transmission lines to reduce their susceptibility to induced currents. Some grid operators have begun installing dedicated geomagnetically induced current monitors on key transformers, allowing them to detect early signs of stress and take protective action before damage occurs. Designs for emergency recovery transformers, intended to allow faster restoration of service after major events, are being refined and, in some cases, prepositioned in strategic locations. None of these developments solve the problem completely, but each of them moves the needle in the right direction, and the cumulative effect over decades could be substantial. The satellite industry is also adapting. New satellites are being designed with improved radiation hardening, more conservative redundancy, and better tolerance for geomagnetic disturbances. Operators of large constellations are developing more sophisticated storm mode procedures, drawing lessons from events like the early Starlink losses I mentioned earlier. The increasing competitive pressure in the satellite launch industry has also driven down costs in ways that, while creating their own concerns about orbital congestion, also make it easier to deploy and replace assets in ways that would have been prohibitively expensive a decade ago. The cosmic forecast does not want to romanticize the satellite industry, but the trajectory of capability and resilience in this sector is, in net terms, positive. There is also a more speculative but increasingly serious conversation about active defenses against major space weather events. This includes ideas such as deploying spacecraft that could detect Earth-directed CMEs at longer ranges than current systems allow, building strategic spare transformer reserves with rapid deployment capabilities, and even, in some of the more far-out research, the theoretical possibility of magnetic shielding for particularly critical infrastructure. None of these ideas is ready for prime-time deployment, and some of them may turn out to be impractical or unnecessary. But the fact that they are being discussed at all in serious technical settings reflects a maturation of the field. We are no longer treating space weather as a curiosity. We are treating it as a manageable problem, and we are starting to ask, in increasingly concrete ways, what real solutions might look like. Beyond the practical engineering questions, the basic science of solar physics continues to advance in ways that I find genuinely thrilling. Permit me, for a few thousand words, to step out of the role of explainer and into the role of something closer to a companion thinker. The Cannibal CME currently colliding with our magnetosphere has given us a chance to talk, on this particular night, about more than just physics and infrastructure. It has given us a chance to talk about who we are as a species when we look up at the sky and try to understand what looking up means. And I would not be doing the cosmic forecast justice if I let that opportunity pass without lingering for at least one full segment on the deeper questions that this kind of event tends to raise in any thoughtful person who watches it carefully. Begin, if you would, with the fact that we are the first generation in the history of our species that can observe these events in the detail we observe them in. For all of the tens of thousands of years that humans have been looking at the night sky, no one before our great-grandparents had any idea that the sun was capable of throwing billion-ton clouds of magnetized plasma at the Earth. For all of the long sweep of human history, the connection between sunspots and auroras and electrical disturbances on the ground was at best a hint, at worst a complete mystery. We are the first generation that can watch these events in real time, model their evolution in interplanetary space, and understand, in considerable detail, the chains of cause and effect that link a magnetic configuration on the surface of the sun to a current induced in a transmission line in our neighborhood. That is, when you think about it, an astonishing privilege. The cosmic forecast considers this privilege a sacred trust, not in a religious sense, but in the sense of being something we are obligated to honor by paying serious attention. It also raises the question of how to feel about the fact that we live in a universe that is, on the whole, indifferent to our well-being. The sun does not throw Cannibal CMEs at Earth because it is angry with us, or because it has been pleased with us, or because we have done anything in particular to invite or deflect its attention. It does so because it is a large ball of plasma whose magnetic field is constantly evolving according to laws that have nothing to do with our existence. The same physics that produces our auroras would produce identical eruptions if our planet were lifeless and unobserved. We are, in this respect, not the center of the cosmic story. We are tiny observers, very recently arrived, very fortunate to exist at all, and entirely beholden to a star that does not know we are here. Some people find this perspective frightening. Others find it humbling. The cosmic forecast, for what it is worth, finds it clarifying. There is a particular kind of peace that comes from accepting that we live downstream of forces much larger than ourselves, that we did not create those forces, that we cannot control them, and that our best response to them is a combination of attentive understanding, careful engineering, and a willingness to take seriously the responsibilities of being conscious creatures in an unconscious universe. That, to me, is the mature position. It is neither the panic position of treating every CME as a doomsday harbinger, nor the dismissive position of pretending that we are somehow exempt from the larger physical realities of our cosmic neighborhood. It is the position of an adult species, slowly figuring out where it actually lives. Consider, also, the question of what space weather risk implies about the way we organize our civilization. Modern civilization is, in many ways, an enormous experiment in deep specialization and tight coupling. We have built systems in which a small number of factories produce critical components, in which a small number of corridors carry critical flows, in which a small number of transformers support entire regions of the grid. This specialization has produced enormous gains in efficiency. It has also produced an unprecedented level of fragility, the kind of resilience that ancient agricultural societies had, distributed across many local communities with locally produced food and energy and tools, has been traded away in favor of the kind of efficiency that modern industrial economies prize. Space weather events expose this trade-off with particular clarity. They show us that the same systems that make our daily lives so comfortable also make our continued comfort dependent on the smooth operation of a small number of vulnerable nodes. The cosmic forecast does not propose that we abandon modernity and return to subsistence agriculture. But I do propose that we ask, more often and more seriously, whether we have given up more resilience than we needed to in our pursuit of efficiency, and whether some careful rebuilding of local capability would be worth the costs it would entail. Consider, also, the question of how this episode of human history will look from the perspective of our descendants. Imagine, with me, a generation that lives 100 or 200 years from now, looking back at our era. They will know, with the clarity of hindsight, whether the early decades of the 21st century were a time when our species took space weather risks seriously and invested wisely, or whether we were a generation that recognized the risk, talked about it endlessly, and failed to act decisively. They will know, with the clarity of hindsight, whether the major events of Cycle 25 and Cycle 26 and Cycle 27 produced disasters that broke us, or near misses that we used as opportunities to build something better. They will know things that we, on this side of the historical line, cannot yet know. Coming back from philosophy to the practical, let us turn now to the question of what to expect over the days, weeks, and months ahead, both in terms of the immediate aftermath of the Cannibal CME and in terms of the broader trajectory of solar cycle 25 and the early years of cycle 26 beyond it. The cosmic forecast wants to leave you with a clear, calibrated, actionable view of the road ahead, so that the next time something like this happens, and there will be a next time, you are not starting from zero. In the immediate aftermath of the current storm, several things are likely to occur. The geomagnetic field will gradually settle back toward quiet conditions over the course of the next day or two, although the recovery is rarely smooth. Substorms can fire off unpredictably during the recovery phase, producing brief renewed surges of auroral activity and elevated induced currents. Grid operators will remain in heightened readiness for at least another 24 hours, and possibly longer, until the geomagnetic indices return to baseline values. Satellite operators will continue to monitor their fleets for delayed effects, such as continued orbital decay, latent radiation damage, and slow recovery of degraded components. Aviation will gradually normalize transpolar routings. Amateur radio operators will begin returning to their usual bands. And in the days that follow, scientific papers will begin to appear, dissecting the event in detail and adding to the long historical record that will inform our response to future storms. In the weeks ahead, the same active region that produced this Cannibal CME will rotate, with the Sun, away from the Earth-facing direction. We will lose direct visibility of that region for roughly 2 weeks, although stereo and certain other off-axis instruments will continue to track it. When the region rotates back into Earth-facing view, we will find out whether it has continued to evolve, whether it has produced additional eruptions on the far side that we did not directly observe, and whether it is likely to produce further Earth-directed events. Meanwhile, other active regions will rotate into view. Some of them will be quiet. Some of them will become active and contribute their own modest events. And a small number of them, if recent experience is any guide, will become the kind of complex, magnetically twisted regions that are capable of producing more major events. The cosmic forecast will be watching every one of them, and we will be reporting back to you on what we see. Over the next several months, we should expect the overall level of solar activity to remain elevated. We are, as I discussed earlier, in what looks like the broader peak phase of cycle 25, with the maximum probably already past us or arriving very soon, and with the active declining phase still ahead. Historically, the years immediately following solar maximum have produced some of the largest individual events in any given cycle, including some of the Carrington-adjacent storms of the past 2 centuries. There is no guarantee that this cycle will continue that pattern, but the statistical tendency is significant. And any responsible space weather forecaster will tell you that the next 2 to 4 years are likely to remain a period of heightened activity. The cosmic forecast is, frankly, going to be a busy channel during that period, and I hope you will continue to be part of this audience as we work our way through it together. Beyond cycle 25, the longer-term outlook is more speculative. Predictions of solar cycle 26 are still being refined, with different methodologies producing somewhat different forecasts. Some indicators suggest that cycle 26 could be even more active than cycle 25, although other indicators suggest a return to quieter conditions. The honest answer is that we do not yet know with confidence what cycle 26 will look like, and the best we can do is continue to monitor the Sun's polar fields, the patterns of meridional flow, and the emergence of new active regions, and to update our forecasts as new data comes in. The cosmic forecast will be there for all of it, and we will keep doing our best to bring you the most honest reading of the evidence as it develops. I also want to talk briefly about what to expect from this channel itself over the months ahead. The cosmic forecast was created with the goal of being a long-term, trustworthy companion to anyone who wants to understand the cosmic environment we live in. That mission has not changed, and it will not change. What will change, hopefully, is the depth and quality of what we deliver. As the audience grows, as we develop more relationships within the space weather and broader astronomy communities, and as the technical resources available for video production improve, my hope is that each episode of this channel becomes a more polished, more carefully researched, more useful resource for you. We will continue to cover major space weather events as they happen, of course. We will continue to do deep dives into historical events. We will continue to talk about the policy and infrastructure dimensions of solar risk. But we will also, I hope, begin to cover a broader set of topics, ranging from exoplanets to gravitational waves to the deep history of our own galaxy, all with the same commitment to honest, calibrated, accessible communication. In all of that, I want to make a commitment to you, and I want it on the record. The cosmic forecast will not sell you fear. The cosmic forecast will not sell you complacency. The cosmic forecast will not chase the easy clicks of catastrophism, And the cosmic forecast will not lull you into the comfortable indifference of pretending that nothing real is happening. 20,000 words is a long way to walk with someone, and yet here we are at the end of the path, with the Cannibal CME still pouring its energy into our magnetosphere. The auroras still rippling across skies that do not usually see them, and the long, mostly invisible drama of infrastructure stress still unfolding above and beneath the ordinary life of every person reading or watching this. I want to use these final pages to close the loop honestly, to gather up the threads we have been weaving together, and to ask you, gently but clearly, to take a few specific actions that I think will matter, both for you personally and for the broader audience that this channel hopes to keep building. The first action is the simplest one. Tonight, if your local weather allows, step outside. Find the darkest spot you can reasonably get to, even if it is only the far edge of your own backyard. Let your eyes adjust to the night for at least 15 or 20 minutes. Look toward the magnetic pole, which is north for most of this audience, south for those of you in the southern hemisphere. And if the Cannibal CME is doing what the forecasts suggest it will do tonight, you may very well see an aurora from a place that does not normally show them. Take a moment when you do to remember that the lights in the sky began their journey on the surface of the sun several days ago, that they crossed 93 million miles of space to reach you, and that you are, in that moment of looking, more aware of the universe you actually live in than the vast majority of humans alive at this hour. That is a small but meaningful gift. The cosmic forecast hopes you will give it to yourself. The second action is to take, in the next few weeks, an honest look at your own household preparedness. Not with anxiety, not with paranoia, just with the calm, practical eye of someone who has now spent 20,000 words thinking about the larger context. Walk through your home and ask yourself whether you are reasonably positioned for a 3-day or 2-week disruption of grid services. Note the gaps. Make a list. Address the gaps gradually, over months, in whatever way fits your budget and your living situation. You do not need to become a survivalist. You do not need to spend a fortune. You need to do the boring, sensible, ordinary work of becoming the kind of household that can ride out a few weeks of inconvenience without becoming a burden on neighbors, on first responders, or on the broader social fabric. The cosmic forecast considers this kind of quiet, decentralized resilience one of the most important contributions any individual can make to civilizational robustness. The third action is more political, although I am going to phrase it carefully because, again, this channel is not in the business of partisan advocacy. Ask of the people you elect and of the institutions that serve you what their position is on long-horizon infrastructure resilience. Ask whether your local utility has a geomagnetic disturbance response plan. Ask whether your country has a national strategy for space weather risk and whether that strategy is being meaningfully funded. Ask whether the spare transformer supply chain in your region is being seriously addressed. Ask whether your aviation and shipping authorities have integrated space weather considerations into their planning. These are not glamorous questions. They will not get you invited to interesting parties. But they are exactly the kinds of questions that, asked often enough by enough citizens, gradually move the slow machinery of policy in directions that matter over decades. The cosmic forecast believes that informed citizen pressure is, in the long run, the most reliable engine of meaningful resilience investment. The fourth action is to keep learning. The Cannibal CME hitting Earth right now is not the last major event you will live through. It may not even be the largest event of this year. The sun is going to keep doing what it does, and the more you understand about the underlying science, the more meaningful and less frightening each subsequent event will be. Watch good educational content. Read books by serious authors in the field. Follow trustworthy researchers and forecasters on social media. Treat your own scientific literacy as a lifelong project rather than a one-time achievement. The Cosmic Forecast hopes to be one of the resources you draw on as you do that, but we are not the only one, and we do not want to be. The more diverse and well-informed your sources are, the better positioned you will be to evaluate any single source, including this one. The fifth and final action is the one I find most personal. Take a moment, after you finish this episode, to share it with at least one other person whose understanding of the universe you care about. Maybe it is a parent who has always been a little nervous about news stories regarding the sun. Maybe it is a child who is just old enough to start engaging with science seriously. Maybe it is a friend who has always been curious but never had the right introduction. The Cosmic Forecast does not grow because of algorithms. It grows because of human beings deciding that this kind of content is worth passing along. If you have made it this far in this 20,000-word episode, you are, by definition, exactly the kind of viewer who can carry the mission of this channel out into the world more effectively than I ever could on my own. I am genuinely grateful to anyone who does that, and I do not say so lightly. Before I let you go, I want to mention, one final time, the channel name that this whole journey has been built around. The Cosmic Forecast,